Okay, so this is the review session for EGME 417, spring 2022 for the first midterm. I looked at the poll just now, and the two winning topics were the two 2D topics. And so we have 2D diffusion and 2D convection diffusion. Right. So the plan is to review these and to have them ready for your midterm. Okay. So let's start with the winning topics. Let's start with 2D diffusion. And so 2D diffusion is basically just our usual conservation equation, but in 2D. Okay, and so a large portion of those notes actually refer to kind of the technical details of writing a program that can solve 2D problems. And so that's not going to be on the exam. So the exam is just going to test to see whether you can discretize these kinds of equations and generate the algebraic equations for those. So just because this is I think the MATLAB programming, of course, is important, but I want to focus this on just skills that are going to be helpful to you on the midterm. So let's just focus on that. Okay. All right. So our 2D diffusion equation looks like the following. So we have partial squared phi partial x squared plus partial squared phi partial y squared is equal to q, which is our source. Okay. And so, trivia-wise, this would be known as a Poisson equation. If you set the source equal to 0, this is a plus. But that's not too important. Okay. What I want to focus on here is how we can discretize these equations. Okay. Okay. And so it's the same process that we've been following for every unit so far, where we take our equation and we replace all the derivatives with their finite difference approximation. Okay. Okay, and so we have two derivatives here, and they're both second order derivatives. And so we're going to replace them with our equation for second order derivatives. Okay, and so first we have partial squared phi partial x squared. And so that finite difference approximation is phi I plus 1 comma j minus 2 phi I comma j plus phi I minus 1 comma j. Okay, all divided by delta x squared. Right, so remember, all of this is partial squared phi partial x squared. Okay, plus we're going to have the same thing but for y. So we have phi I j plus 1 minus 2 phi I comma j plus phi I j minus 1. Okay, all over delta y squared. Okay, and so this is partial squared phi partial y squared, and of course all this is equal to q. Okay, right, and so let's talk about this notation a little bit, because the i's and j's are important. And so remember, the way that we apply this equation is that we have our two-dimensional grid. And so our two-dimensional grid is comprised of nodes in that kind of nodal structure. Okay. And so when I say that we're going to apply this finite difference approximation to a particular node, what I mean is this. Okay, and so the node that we're actually applying it to, we'll call it node I comma j. Okay. Okay. And so let's say that I'm going to apply this to an arbitrary node number. So let's say I'm applying it to node number 6, and so phi at I comma j there would be phi 6. Okay. And then, in order to complete this finite difference approximation, we need neighbors on each of the sides of our node. Okay, and so we have our right neighbor, and so our right neighbor has an I plus 1. Our left neighbor has an I minus 1. Our upper neighbor is a j plus 1. And our lower neighbor is j minus 1. Okay. Okay. And so kind of keep that in mind as we kind of go through these derivations, what each of the i's and j's and their plus 1 and minus 1 variant, what they refer to. Okay. All right, so that's our full equation right there. And so usually what we do is we simplify this a little bit just to make it a bit easier, because usually it's a little bit hard to work with fractions, and so especially with the delta squared in the bottom. And so what I like to do is I like to move the delta out of the denominator by multiplying both sides of the equation by the grid spacing. Okay. Oh, and we usually assume that delta x and delta y are the same. Right. So this step is actually optional, and so whether you have it in this form and or whether you keep the deltas in the denominator, it's up to you. It's really kind of a personal preference. But just for me, I like to keep my number of fractions to a minimum, just for because it saves some time writing, it saves some time computing, and so I like to multiply through. But you don't have to do this. Okay. And you'll see that even more in convection, that how you arrange the equation is kind of really up to your personal preference. But there's no wrong way to do it. And so if you do choose to arrange your equation in a certain way, as long as you're consistent with your algebraic manipulations, and so you don't kind of forget to multiply one side by delta or delta squared, it's all good. And so it's all fine. And so you'll get full points for it either way, as long as all the math for it is correct. Okay. But for me, I prefer to move the deltas to the other side, and so let's go ahead and do that. Okay, and so if we go ahead and do that, then what we're left with on the left-hand side, we have phi I plus 1 comma j plus phi I minus 1 comma j comma j, okay, minus 2 phi I comma j, okay, plus phi I comma j plus 1 plus phi I comma j minus 1 minus 2 phi I comma j is equal to q delta squared. Okay. Right, and so the delta squared came over to the other side because we multiplied both sides of the equation by it. Okay. And so let's simplify this a little bit. And so we have a common term here, so we can go ahead and combine it together. And then after doing so, we get the familiar finite difference equation for 2D diffusion. Okay, so phi I plus 1 comma j plus phi I minus 1 comma j plus phi I j plus 1 plus phi I j minus 1 minus 4 phi I comma j is equal to q delta squared. Okay, so this right here is our finite difference equation, or finite difference approximation for 2D diffusion, okay, with the source. This process that we just went through, so we started basically with this differential equation right here, okay, and the process of replacing the derivatives with their finite difference approximations, this is important. And so this is something I expect you to be able to do on the exam, because it's a core, it's a fundamental kind of skill, fundamental piece of knowledge that I want you to take away from this class, of how to form these types of approximations. Okay. And so, don't just skip to the box equation here. Okay, so I want you to be able to derive these equations. Okay, and the example tells you to do so as well. So the example tells you, starting from the full differential equation with its full derivatives and such, plug in the finite difference approximations in order to get the equation that you want in the end. Okay, so you can't just skip to this. You need to do the full process here. Okay, all right. And so how do we actually apply this in general? Okay, and so kind of like how I mentioned, this is kind of based off the 5-point stencil that we have up there, right? And so what you can do, because you're going to be applying these by hand, if it helps you, instead of having I plus 1j, I minus 1j, ij plus 1, so stuff like that, you can replace these with a tagline that indicates which neighbor that these phi values refer to. Okay. And this, I think, will help you out a bit too. At least cut down on some of the mental processing that you have to do on the exam. Okay. Okay, so let's look at I plus 1 comma j, right? And so if we go back to our stencil up here, okay, we can see that I plus 1 comma j is the neighbor that's immediately to the right. Okay. And so if we take that in consideration, we can go ahead and replace this I plus 1 comma j, and instead we can say that this is for the right neighbor. Okay. I had to delete some of the plus there. Okay. Right. And so same thing for I minus 1 comma j. So I minus 1 comma j. Go ahead and erase this really quick. Okay. I minus 1 means we're 1 to the left of our chosen node, and so this will be phi left. Okay. I deleted the plus sign again. Okay, next we have phi I plus 1 comma j, or phi I j plus 1. So let me go ahead and delete this as well. Okay. And this one, if we're j plus 1, that means we're above our chosen node, and so this will be phi up. Right. And then next we have phi I comma j minus 1, and so j minus 1 will be our bottom neighbor, and so this will be phi down or phi below. Okay. Okay. And of course, phi I comma j, this is our chosen node. Okay. And so this will be the center node. Okay. Okay, so that's going to help us because usually these problems, part of the problem that you're going to get is to do this process, right? So filling out the finite difference approximations, but I also want you to apply this as well. All right, so here is our typical 2D domain, okay? And so this domain in particular has 16 nodes. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, okay? And so, I would, after you obtain the equation above, I would say, let's go ahead and apply this to some of the interior nodes. Okay. In particular, I'm usually going to give you a node number for this because there's 16 nodes, and I can't ask you to write 16 equations on the exam because that would be a little bit too much. Okay. And so let's say, for instance, that I want you to apply this on node number 7. Okay. Okay. And so you're going to apply the equation from up here, to that node 7. So you're going to plug in the ID numbers for the left neighbor, the right neighbor, the up neighbor, the down neighbor, as well as the center one. Okay. All right, so let's go ahead and start. And so we have first our equation starts with phi right, okay? And so the neighbor that's immediately to the right of 7 is phi 8, okay? All right. Next we have phi left, and so the neighbor that's immediately to the left of node 7 is node 6, and so this is phi 6. Okay. Then we have the neighbor that's immediately above this node, and so that's going to be phi 11. And then we have the node that's immediately below it, and so that's going to be phi 3, right? So, excuse me. And so all of these nodes are being measured relative to our center node, which is 7. Okay. And then we have -4 times phi of the center node. And so phi center here is 7. Okay. And of course, this is equal to q I comma j, which is our source term, multiplied by delta squared. Okay. Okay. All right. So let's talk about the two other things I want to talk about in this unit are things like the boundary conditions and things like the source terms. But let's talk about the source term first, because that's since we have that right here. Okay. And so oftentimes your source term here is going to depend on the coordinates x and y. Okay. Okay. Delta. And let me kind of show what delta means. So remember, delta is always our grid spacing, and so delta is always going to be the space or the physical distance in between the nodes in our grid. Okay. And so this distance right here, this is delta. Okay, and if we assume that delta x, delta y are the same, that means that that distance is also delta right there. Okay. Okay. So let's talk about the source term. So the source term q here is given usually in terms of functions of x and y. And so just as a simple starting point, let's say that our q of x and y is equal to just the product x times y. Okay. And so if I were to replace that here, okay, then our source function here would be xi times yj. Okay. Where x and y here, x and y are the coordinates of the center node. Okay. The center node here being node number 7. Okay. And so remember, we talked about that when you're doing these 2D problems, you have to know what the I and J coordinates for each of the nodes are, but you also have to know what their physical coordinates are. Okay. And the way to get their physical coordinates is to count, how many deltas there are, from the origin to that space. Okay. And so let's take node number 7. Okay. Again, keeping in mind that the grid spacing is delta, right? And so let's compute the x coordinate of point number 7, as well as the y coordinate of node number 7, under the assumption that our node 1 here, node 1 is at the origin. So node 1 is 0, 0. Okay. And so for node 7, the x coordinate, for node 7, we need to count how much we can move horizontally across. And so we can see here that we move a distance of delta right here, okay? And then we move another distance of delta to get to the horizontal location. Okay, so the x coordinate here is going to be 2 times delta, right? Because that's how many deltas we have to move horizontally to get to node 7's horizontal position. Okay. Whereas the y coordinate the y-coordinate here, you can see we only have to go up by 1 delta, right? And so we start at the origin and we go up, okay? And we're already in line of node number 7. So the y-coordinate here is just going to be delta, okay? And so if I were to rewrite this equation, with that knowledge in mind, we can have, our expression, our full expression for this. Okay? Right, so everything on the left-hand side of the equation, that just comes down because there's no change in that, okay? Next, we have xi. So xi, we're going to plug in the x-coordinate, and so that's going to be 2 delta, okay? Next, we have yj. So yj is going to be the y-coordinate, so that's going to be just delta, okay? And then we have the delta squared, which came out from our finite difference approximations way back kind of earlier in the process, okay? And so if you multiply all this together, you get 2 times delta to the 4th power. Okay, so this is going to be phi 8 plus phi 6 plus phi 11 plus phi 3 minus 4 times phi 7. Okay. All right, and then depending on the value of the grid spacing, you can kind of simplify this further. And so let's say, for instance, that the grid spacing was 1/2. Okay. Or 0.5, okay? Then our right-hand side here would be 2 times 0.5 raised to the 4th power, okay? And so if you work through the math for that, that is about 1/8, okay? All right, so that's how you handle the source terms. And so remember, the source terms are usually given to you in functions of x and y. And so all you have to do is just plug in the physical x and y coordinates of the node that you're solving for. Okay. Okay, so that's source terms, right? And so make sure you know how to do that for the exam, because that's going to be important. And so the next thing that we're going to have to work on is boundary conditions. Okay. And remember, boundary conditions, they define the solution behavior at the boundaries of our domain. Okay. And so for 2D problems like this, we have 4 main boundaries that we need to worry about. Okay. And so we have the north boundary, we have the east boundary, the south boundary, and the west one. Okay. And so usually when you're given these kind of 2D problems, they're usually given to you in the following form, right? And so I'm going to give you the domain. Okay, so the domain's always going to be a square. Okay. And then I'll show you, what the boundary conditions look like on each of the boundaries of our domain. Okay. And so let's just say, for instance, let's say that we have a Neumann condition like this. Okay. Okay, and so let's get a little variety. So let's do kind of a little bit of everything. Okay. And so what I'm going to ask you on the exam is to, first of all, tell me, for each of the boundaries of the domain, what type of boundary condition do we have there? Okay. Okay. And so let's go through this example right here and label what each of the boundary condition types are like. Okay. So let's start with the north. And so the north right here, you can see we have a boundary condition called partial phi partial n is equal to 0. Okay. Since we have a boundary condition here on the derivative of phi, then then we have Neumann type boundary condition. Okay. Okay. All right. So that's the north. That's the north boundary. Since it's a derivative type boundary condition, we have a Neumann there. Okay. Next, let's kind of work our way clockwise around the domain. Next, we have east. Okay. And so the east boundary condition you can see here is phi is equal to 1, right? And so here we're directly specifying the value of our solution variable. And so remember, these types of boundary conditions are called Dirichlet. Okay. Okay. Working our way around the horn, next we have our south boundary condition. Okay. And so the south boundary condition here, we're directly specifying the value of the solution. And so we're saying phi is equal to 4. And so this is also going to be a Dirichlet boundary condition. Okay. All right, finally we have the west boundary. And the west boundary, you can see here we have a boundary condition on the derivative. We have partial phi partial n is equal to 5. And so this is a Neumann type boundary condition. Okay. So that's the first thing I would want you to be able to identify. So I want you to be able to identify, what types of boundary conditions are going to be applied on each boundary. Okay. Given a problem, I want you to be able to label it well. Okay. The next thing I want you to be able to do is I want you to be able to write out the algebraic equations that actually specify these boundary conditions. Right, because each of these boundaries they're going to have nodes that sit on their boundaries. Okay, and so when I say the algebraic equations, what I mean is the nodal equations for the nodes that sit on these boundaries. Okay, and so let's just, for the sake of argument, let's say that we have phi2 there. This is going to be node number 1, 2, 3, 4, 5, 6, 7, 8. Okay, so this is going to be number 8. I mean, there are going to be multiple nodes, right? And so if we look back at the domain up here, we have multiple nodes that are on these boundaries. But I would only, but as soon as you give me kind of one solution for that, then that's good. And then I know you can apply it for the rest of them too. Okay. So I'm just going to do one example per boundary just to kind of show you what they look like. Okay. All right. Phi5, and since this was a Neumann, we also need phi6. That's going to be right immediately next to it. Okay. And then up top right here, let's do phi. Okay, so up top here, let's do phi15, and the one on the interior is 11. Okay. And so when I ask you to write out these equations, these are the equations that actually go into our left-hand side matrix and right-hand side forcing vector to solve these equations, computationally. Okay. So let's start with the easiest one and kind of work our way around. So let's start with the bottom boundary, okay? Or the south boundary, I should say. And so the south boundary, you can see here we have a Dirichlet boundary condition, okay? And so for Dirichlet boundary conditions, remember we just directly specify the solution value. And so one such node on the south boundary here is node number 2, okay? Okay. And so since the Dirichlet boundary there is that phi is equal to 4 on everything on the south boundary, then we can say phi 2 is equal to 4. All right, so next let's do the east boundary. And so the east boundary is also a Dirichlet type boundary condition, right? And one such boundary on the east boundary there is node number 8, okay? So we have phi 8. This is going to be equal to whatever the Dirichlet value is on that boundary. So on that boundary, our Dirichlet value is 1, okay? Okay. And so that's the boundary condition that we're going to apply there. Next, let's go up top. And so this is going to be our north boundary. Okay. And so our north boundary is a Neumann type boundary condition. And remember, whenever we have a Neumann type boundary condition for a 2D case, they follow a very strict protocol, or not a strict protocol, but they follow the following algorithm. Okay. Okay. And so we're going to take the difference of the inner node on that neighbor minus the boundary node divided by the grid spacing, okay? And that's going to be equal to the Neumann value. Okay. Okay. All right, so let's go ahead and apply that for this boundary here, okay? And so you can see here for the north boundary, I've drawn in a pair of nodes, okay? So we have phi 15 that's on the boundary. Okay. And then its inner neighbor, or the neighbor that's kind of right, next to it, that's in the interior direction, is node 11. Okay, so let's go ahead and fill into that this equation here. And so we have phi inner, and so phi inner here is going to be phi 11, okay, minus phi boundary. So phi boundary here is going to be phi 15. Okay. We divide that by the grid spacing, and this is equal to the Neumann value, which for the top boundary is just going to be 0. Okay. And so the Neumann boundary, when I say Neumann value, that's the value that the problem specifies that we want to set equal to the derivative. Okay. And so this is going to be equal to 0. We can simplify this a little bit. We can multiply both sides of this equation by delta. Okay. And so we do that. We have phi 11 minus phi 15 is equal to 0. All right, so that's the north boundary. Oops. All right, and then finally we have the west boundary. So west boundary is also a Neumann type boundary condition. And so we're going to use the same framework that we have up there. Okay, so we have phi inner minus phi boundary. Okay, is equal to gamma divided by delta. Right. And so let's look at the domain for the west boundary. So for the west boundary, the node that I've drawn here is node 5. And so node 5. So 5 is boundary node. Okay. Its inner neighbor here is going to be the one immediately to the right of it. So that's going to be phi 6. Right? Yeah, 5 and 6. Okay. And for this boundary in particular, we can see that the Neumann value is 5. Okay. So the Neumann value is 5. Okay. All right, so we plug all these things in, and so we have phi inner, which is 6, minus phi boundary, which is 5, divided by delta is equal to 5. Okay, and so we multiply delta by both sides, and we get phi 6 minus phi 5 is equal to 5 delta. Right, and so that's an example of an algebraic equation that you would apply on the Neumann boundary on the left. Okay, when you have a non-zero Neumann value. Okay. All right, and so that's kind of a crash course in everything that you need in terms of 2D diffusion. Okay. Next, we're going to move on to 2D convection. Okay. Where a lot of it's going to be more or less very similar. Okay, and so just like we did with diffusion, let's go ahead and start with the full equation. Let me just go ahead and pull that up in my notes. Okay, and so our 2D convection equation, this is going to be a little bit more general than before, okay, because I'm going to include a diffusion coefficient. And so we have k multiplied by partial squared phi, partial x squared, plus partial squared phi, partial y squared, is equal to u partial phi partial x plus v partial phi partial y, okay, plus q. Okay, where these guys here are our diffusion terms, these are our convection terms, okay, and this is q, source term. Okay. All right, and so the first step, just like the first step that we did with 2D diffusion, is to discretize this equation. Okay. Okay, and so just like we did with diffusion, you know, we can plug in the finite difference approximations for each of those derivatives. Okay. But before I do that, there is an added level of complexity to any kind of convection problems, and that has to do with the fact that, you know, our convection derivatives can go unstable under certain situations. Okay. Okay. Right, and so it depends. I mean, it depends on a few things. So it depends on, you know, what the grid spacing is. It depends on you know, on the type of differencing scheme that you use, and so there's a lot of things that can happen here. Okay, and so the simplest thing to do is to just apply a central difference scheme. Okay, and so remember, you know, whenever we have convection, we kind of have two paths that we can take. And so the first path is, of course, we can just use central difference. Okay, and so central difference here will lead to a scheme that's second order accurate. Okay, but you know, the thing with central difference is that you might have an unstable solution if your Peclet number is greater than 2. Okay. So remember, the Peclet number is, excuse me, Peclet number here is the velocity. Okay. You can just go ahead and take the absolute value of the velocity. So even if the velocity is negative, you can just you know, take the absolute value. You're going to multiply by the grid spacing, and you're going to divide it by the by the diffusion coefficient, okay? And so if this number is less than 2, that means you have a stable solution. And so that's good, okay? And so practically speaking, you're a lot of times you're going to be given a problem like this, and you need to see, you need to be able to check and see, whether your solution is going to be, stable, okay? Because in all honesty, most of the time, if you can have the grid spacing for it, the grid spacing small enough, it's usually a pretty good idea to have a central differencing scheme, because the accuracy is just better, okay? And so if you do have an accurate, or if you do have a stable solution, if your Peckway number is less than 2, then I would say go ahead and use central difference, okay? But you need to check it, right? And so you need to check, whether your solution here is going to be stable, under these conditions and under that following grid spacing, okay? Because usually for these problems you're going to have everything that you need, and so you're going to have the convection velocity that's given to you in the problem. You have the grid spacing, because that's going to be given to you in the problem as well, and the diffusion coefficient also is going to be given to you in the problem. Okay, so you should be able to compute kind of right away whether your scheme is going to be stable with a central differencing scheme. Okay. The other technique that you can do is you can use upwinding. Okay, and upwinding will always result in a stable solution, but you have to make sure you upwind in the right direction, right? So upwinding means that we either use a forward difference or a backward difference for our derivatives. Okay. And whether you use a forward or backward difference depends on the sign of the velocity. Okay. Okay. And so if our velocity is positive, then the proper upwinding scheme here to use is a backward difference. Okay. But if the velocity is negative, then the proper scheme to use is a forward difference. Okay. But both of these kind of have the downside is that they're only going to be first order accurate. Okay. All right. And so if the problem gives you, basically if the problem gives you a velocity that's very, very high, so you have a very high convection velocity, unless your grid is really, really fine, then you're probably not going to have a stable solution. And so in those cases, you're going to have to rely on upwinding to get you to a stable solution. Okay. But with the downside being that it's only first order accurate. Okay. And just make sure that you apply the appropriate differencing scheme based on the direction of the velocity. Right? And so there's a lot of decisions that you have to make. And so there's, you should make these decisions kind of before you actually start discretizing the equation. Okay? Okay. All right, and so with that said, let me go ahead and run through the discretization here. Okay, and I'm going to do it under the assumption that we have a fine enough grid, or velocities are small enough, and so for this derivation, I'm going to use central difference. But again, you want to make sure that you check beforehand, whether you can use central difference or not. Okay. All right, so let me go ahead and pull up the equation again. Where'd it go? Okay. Okay, and so I'm going to replace all the derivatives here with their appropriate finite difference approximation. Okay, so let's start with the diffusion derivatives. And so we have phi I plus 1 comma j minus 2 phi I comma j plus phi I minus 1 comma j, right? All divided by delta squared, where again, we're assuming the grid spacing is uniform. Okay, where this guy right here came from partial squared phi partial x squared. This guy right here came from partial squared phi partial y squared. Okay, is equal to u times, and this is where you plug in your convection derivative. And so for this one, I'm using central difference. So this would be phi I plus 1 comma j minus phi I minus 1 comma j, all divided by 2 delta. Okay, plus phi I j plus 1 minus phi I j minus 1 divided by 2 delta. Okay, I forgot the v, so the v goes out in front. Okay, plus q I comma j. Okay, for this one, got this guy right here. This is partial phi partial x. Okay, and this guy right here was partial phi partial y. Okay, all right. And so now let's go ahead and simplify. And so I'm going to multiply the entire equation by delta squared. Okay. And so if we do that, and I'm gonna go ahead and simplify terms a little bit. Okay. We have k times phi I plus 1 comma j plus phi I minus 1 comma j plus phi I comma j plus 1 plus phi I comma j minus 1 minus 4 phi I comma j. Okay, this is equal to u delta divided by 2 times phi I plus 1 comma j minus phi I minus 1 comma j. Okay, plus v delta divided by 2 times phi I j plus 1 minus phi I j minus 1. Okay, plus q I comma j delta squared. Okay. All right, so we're almost done, and so let's go ahead and move all the phi terms to the other side of the equation. Okay. All right. And so if we do that, we have all of the convection phis. We're going to move to the other side, and I'm going to group them all together. Okay. Okay, so we'll start with phi I plus 1, and so we have a k minus u delta divided by 2 times phi I plus 1 comma j plus, we have phi I minus 1 now, we have k plus u delta divided by 2 times phi I minus 1 comma j. Okay, plus k minus v delta divided by 2 phi I comma j plus 1 plus k plus v delta divided by 2 phi I j minus 1. Okay, minus 4k phi I comma j is equal to q I comma j delta squared. Okay. All right, and there is our finite difference approximation for our convection, our 2D 2D conservation equation with convection and diffusion. Okay, and so again, don't just skip to this part right here. I mean, you can use this to check your answer because on the exam, you'll be given kind of numbers for all the diffusion coefficients and the convection velocities, but you can't just skip to here. So I want you to go through this process here of like, you start with the equation, differential equation, you plug in the discretization, all the finite difference approximations, and then you work through the algebra of actually, putting it into a usable form where you can apply this to your grade. Okay. Okay, and so I think that's everything that I wanted to talk about in terms of 2D convection diffusion. So that should give you a good overview of what to expect. I mean, first of all, a good review of these topics and a good overview of what to expect on the exam regarding these topics. Okay, and so if you have any other questions, regarding the exam or anything, please don't hesitate to reach out. And so, we still have a few days. But as of recording this video, we still have 5 days until the exam. So, once questions come up, just shoot me an email, and I'll do my best to try to respond as quickly as possible. All right. So best of luck studying, everybody. Have a great weekend, and I'll see you next week.